How do you build a district full of skyscrapers where there's literally no land at all? You need to weld together a platform from 100,000 tons of steel right above trains racing at full speed. That's exactly what was done in New York City, and today I'm going to show you how this is practically possible. So I'm standing on Hudson Yards, a new neighborhood in Manhattan where skyscrapers are literally suspended in mid-air. Beneath my feet is a rail yard that's still in operation. Right now, as I'm speaking to the camera, trains are moving around down there. This isn't a metaphor or an exaggeration. There literally is no ground here. Just steel, concrete, and the brilliant insanity of American engineering. Let's first figure out what was actually happening here before all of this appeared. On this site, between 10th and 12th Avenues, between 30th and 34th Streets, sat an open rail yard operated by the Long Island Railroad. Open meaning outdoors, no roof, no covering. Just peripheral railroad tracks with trains shuttling through every day. The area of this yard is roughly 28 acres. That's a massive chunk of land in the most expensive city on the planet, just sitting there doing nothing except letting trains pass through. Developers from related companies spotted this gap back in the 2000s and decided, this will be a city, not a park, not a stadium. A city with skyscrapers, offices, shopping centers, restaurants, and apartments worth insane money. Total project budget, $25 billion. This is the most expensive private real estate development in United States history. To put that in perspective, with that kind of cash, you could buy several mid-sized cities in another state and still have pocket change left over. But there's one tiny problem: land. There isn't any. Under your feet, train tracks. And before they could put up even one skyscraper, engineers had to solve a problem with no obvious answer. How do you build a foundation where there's nowhere to build a foundation? The answer: a platform. A massive steel platform built over an active rail yard. But first, piles. And this is where it gets really interesting. To support the future platform and everything that would grow from it, engineers designed a system of steel caissons. A caisson is, simply put, a giant hollow tube made of thick steel. It's driven or drilled into the ground, then filled with concrete. The result is a super strong pile. At Hudson Yards, these tubes measured up to 6 feet in diameter, and some extended into Manhattan's bedrock more than 100 feet down. You must never forget, Manhattan sits on granite. That's one of the main reasons skyscrapers can even be built here. The rock holds. But drilling through that rock and driving steel tubes into it, that's no job for the faint of heart. Now imagine you have to do all this on an active rail yard. The trains didn't stop. The Long Island Railroad is the lifeblood of Long Island and parts of New Jersey. Every day, trains pass through this depot. Stopping them isn't an option. So the builders had to work between the tracks, above the tracks, around the tracks, all without touching the trains themselves. Every drill rig, every crane, every column had to be calculated so it wouldn't cross paths with the train routes. This was a three-dimensional puzzle where one wrong move could lead to disaster. In total, Hudson Yards had over 300 of these steel caisson piles installed. 300 stakes driven into Manhattan granite, each filled with concrete, each designed to bear tens of thousands of tons of load. That's the foundation of what I'm standing on right now. But the piles are just the beginning. Now you've got to put something on top of them. And that's where steel enters the scene in quantities that'll make your head spin. The Hudson Yards platform required about 100,000 tons of steel. Seriously. The deck over the rail yards alone weighs more than one of the world's most famous skyscrapers. Steel came from different plants all across the country. From Indiana, from Pennsylvania, from Arkansas. Massive beams and trusses traveled by truck and rail to end up here in Manhattan. But getting the steel to New York City, that's only half the battle. The real headache started when you had to lower these structures into place. Trusses, They're welded steel structures in a triangular shape, like giant metal sandwiches. They support the main platform, transferring the load from the skyscrapers down to the piles. Some of these trusses weighed several hundred tons each, and they had to be lowered over moving trains. How'd they do it? At night. The railroad gave the construction crews a narrow window, a few hours between the last night train and the first morning train, usually somewhere between 1 and 4 in the morning. 3 years. In that time, they had to bring in the crane, lift a truss weighing hundreds of tons, position it precisely between the piles, lower it into place, and lock it down. And then, the crane had to show up, get in there, and reach that first train. I'm not kidding. If the crane didn't clear the tracks before service started, trains couldn't leave the depot. They determined exactly where the crane would sit, at what angle they'd lift the truss, what the next steps were. Night crews rehearsed these operations during the day on mock-ups. And then, when night came, everything had to go off without a hitch. Again and again, night after night, for several years. Trains stopped, trusses lowered, the crane rolled out, trains kept moving. No one knew what was happening up above. Passengers sat in train cars, scrolling through their phones, not even realizing that a whole new New York neighborhood was being built right above their heads. The total platform area, about 3.5 acres in the first phase of construction. That's not the entire neighborhood. Hudson Yards is being built in stages, and some of the skyscrapers stand on good old solid ground where it exists. But the main focal point, the first site with the towers of 30 Hudson Yards and 35 Hudson Yards, that's the section over the rail yard, where the steel platform carries all the weight. 30 Hudson Yards, a skyscraper standing 1,282 feet tall. That's 66 floors, and it's the second tallest building in New York after One World Trade Center. On the 75th floor, there's an observation deck called Edge. It partially hangs over the street with a glass floor. I stood there, looked down, and tried not to think about the fact that underneath all of this, there are trains. This entire engineering feat, all this steel, all these nighttime crane operations, this isn't some showpiece. It's a forced solution. Manhattan doesn't grow outward. It's been built up for ages. Every free patch of land here is either already occupied or costs insane money. They had to figure out how to use this space without stopping the railroad. And they figured it out. They lifted the city above the railroad. They drove some of the steel piles into granite. They hauled steel from across the country. They lowered massive trusses over trains in the middle of the night. And now there are skyscrapers here, where people live, work, and eat lunch, even though their entire neighborhood rests on 300 piles driven into bedrock and 100,000 tons of steel. I always say the most interesting things in cities aren't what you see. It's what's hidden beneath your feet. And here at Hudson Yards, beneath your feet lies an entire railroad. And above it, a $25 billion neighborhood that's slowly changing the face of New York. That's all for today. If you enjoyed this, hit that like button and subscribe, because there are tons more places coming up where engineers pulled off what seemed impossible. Today, we're at a factory that produces true marvels of engineering, deep water drill pipes, or as they're also called, risers. Look at this pipe. It'll be hanging from an oil platform nearly 10,000 feet underwater. That's almost 2 miles down, through the ocean depths where the pressure can crush a car in seconds. And these pipes have to withstand not just the ocean pressure from the outside, but also the pressure of drilling fluid and oil on the inside, plus their own weight of 1 ton. Let's see how these incredible structures are made. I'm standing right now next to a riser blank, a solid steel cylinder 9 inches in diameter and 12 feet long, weighing over a ton. From this thing, they'll make a seamless pipe 21 inches in diameter and about 50 feet long. Yeah, you heard that right. A massive pipe comes out of this small blank and all of it without a single weld. The absence of welds is what makes risers so incredibly strong. First stage, heating the blank, or as they call it, the billet. The billet gets loaded into a rotary furnace and heated to 2,250 degrees Fahrenheit. That's so hot, the steel glows bright yellow and softens like clay. Heating takes 2 hours. You need the temperature to be uniform along the entire length of the billet. Right now, the most incredible process begins. Piercing using the Mannesmann method. Check out this machine. It's a piercing mill with 2 massive barrel-shaped rolls. The hot billet sits between the rolls, which rotate in the same direction, but are angled at 10 degrees to the billet's axis. This creates a spiral motion that literally tears open the billet's center. What happens is called the Mannesmann effect. When the billet rotates under pressure, tensile stress develops at its center, leading to crack formation. At that moment, a water-cooled mandrel, a cone-shaped tool, is inserted into the center. The mandrel pushes through the billet, expanding the central crack and forming a hole. In just seconds, a solid steel cylinder transforms into a thick-walled tube called a bloom. The bloom exits the piercing mill, glowing white-hot, its length tripled, from 12 feet to 36 feet, with a 5-inch diameter hole now running through its center. But this is only the beginning. The shell has a wall thickness of about 2 inches, way too thick for a riser. It needs to be stretched out and the wall thickness reduced. Next, the shell moves to a floating plug mill. This is 8 sequential rolling stands, where the rollers are positioned at 90 degrees to each other. A long mandrel is inserted into the shell, a steel rod 65 feet long, coated with graphite lubricant. The mandrel floats inside the pipe, controlling the inner diameter during rolling. The process looks incredible. The shell passes through the stands where the rollers squeeze, stretch, and twist it all at once. With each pass, the wall thickness decreases and the length increases. Sparks fly everywhere. The hot metal glows orange. In 30 seconds, the shell transforms into a 50-foot pipe with a wall thickness of 0.875 inches. After rolling, the pipe needs to be reheated. Why? Because during rolling, the metal cooled and hardened unevenly. The pipe is loaded into a furnace and heated again to 1900 degrees Fahrenheit. It's held at this temperature for 2 hours. This is normalization, which evens out the metal structure and relieves internal stress. Then the pipe passes through a reducing mill, a series of rollers that bring the outer diameter to a precise 21 inches. At a speed of 30 feet per second, the reducing mill shapes the pipe's final dimensions. After hot rolling, cooling begins. The pipe can't be cooled quickly, it'll crack, so it's stacked on special racks and left for 4 to 6 hours. Slow air cooling brings the temperature down to 300 degrees. Then the pipe can be cooled with a water mist. Now the most precise stage, straightening and machining. Check out this straightening station. It's got several rollers that work the pipe, correcting any bends. Next up, end finishing. Special lathes cut the pipe ends at perfect right angles, accurate to 1/1000th of an inch. Mechanical couplings get welded to each end, specialized connections that let you quickly join riser sections on the drilling platform. These couplings are made from the same high-strength steel and feature complex threading and sealing. But the final stage, heat treatment. The pipe needs to be strong, but not brittle. It gets heated again, but this time only to 1600 degrees Fahrenheit and held there for 2 hours. The water's then rapidly cooled from 1800 degrees down to 300 in 30 seconds. That's quenching. It transforms the steel structure into martensite, a super hard form. After quenching comes tempering. The pipe's heated to 800 degrees Fahrenheit and held there for 4 hours. This removes brittleness while keeping strength. Final yield strength? 80,000 pounds per square inch. Hardness? 45 to 50 on the Rockwell B scale. the perfect balance of strength and ductility. Now here's why these pipes are so special. At 9,000 feet deep, water pressure hits 4,000 pounds per square inch. That's like stacking 4 compact cars on every single square inch of the pipe's surface. And inside the pipe, drilling mud circulates at pressures up to 15,000 pounds per square inch. This pressure differential creates massive stress on the pipe walls. Plus its own weight. A riser section 50 feet long weighs about 4,000 pounds. To create a column 9,000 feet deep requires 180 of these sections. Total weight, 720,000 pounds, or 360 tons. And all these loads are held by the upper sections, plus special tensioners on the platform. Quality control here is absolute. Every pipe gets ultrasonic inspection for internal defects. Even a defect 1/8 of an inch in size can lead to catastrophic failure under pressure. They also use magnetic particle inspection, magnetic powder applied to the surface that reveals microcracks less than 0.02 of an inch deep. Next, hydrostatic testing. The pipe gets filled with water and subjected to 15,000 pounds per square inch of pressure. That's more than operating pressure. They hold it under pressure for 30 minutes, monitoring for any leaks or deformation. If the pipe passes, it's ready for service. Special attention goes to collapse resistance. That's the pipe's ability to withstand external pressure without imploding. Calculated using complex API5 C3 formulas that factor in diameter, wall thickness, and material properties. For depths of 9,000 feet, collapse resistance must be at least 4,500 pounds per square inch. Interesting thing, for ultra-deep water programs, over 15,000 feet, they use innovation. Shrink-fit connections instead. They heat the coupling to 1,500 degrees, slide it onto the pipe, and when it cools, the connection becomes stronger than a welded joint. This allows using capital with strength up to 110,000 pounds per square inch. They also simulate millions of platform bending cycles that occur from wave motion. The pipe must withstand 10 million bending cycles under load without forming secondary cracks. That's the equivalent of 25 years of operation. A single riser 50 feet long costs anywhere from $60,000 to $120,000 depending on the specs. For a system 9,000 feet deep, you're looking at close to $20 million just in pipe. But without them, there's no way to drill in deep water shelf areas where massive oil and gas reserves have been discovered. And without you, there's no way my YouTube channel can grow, so I'm inviting you to subscribe. Every year, the world burns through over 100 billion gallons of fuel, but nearly half the energy for the east coast of the United States flows through a single steel artery stretching over 5,000 miles. Colonial Pipeline, a tube just 3 feet wide that pumps more than 100 million gallons of gasoline, diesel, and jet fuel every single day. Without it, gas stations shut down, prices skyrocket, and panic sets in. In 2021, one cyberattack nearly paralyzed half the country. How does this silent system actually work? What's hidden inside that dark pipe, where pigs weighing hundreds of pounds roam free? And what's the weak link that could change everything? Stick around till the end. You'll see the invisible machine that fires up millions of engines every day. Today, we're standing next to one of the most invisible, but absolutely critical pieces of infrastructure in the United States. A system without which millions of cars simply wouldn't move. What you're looking at is the Colonial Pipeline, a massive fuel artery that pumps energy every single day to half the country. It's not a factory, not an oil rig, not a port. It's a pipe. Steel, buried underground, silent. But it's what keeps modern life moving. A metal cylinder, roughly 3 feet across. The total length of this system? Over 5,000 miles. That's farther than the entire width of the continent. And inside this pipe, millions of gallons of gasoline, diesel, and jet fuel flow every single day. The coolest part is when you learn there aren't separate pipes for each type of fuel. Everything goes through the same route. Regular, premium, diesel, jet fuel, all moving down the same steel highway, but not mixed together. They travel in batches, one after another. First, say, a batch of regular gasoline. Behind it, a batch of premium. Then, diesel. Between them are thin transition zones where the fuels mix a little. These zones are carefully tracked and then separated at terminals, so not a single drop ends up where it shouldn't. To keep this flow moving, you need force, and that's where pumping stations enter the game. Along the pipe route sit dozens of powerful complexes. Each one looks like a small industrial yard with tanks, electric motors, pipes, and control panels. Inside, pumps capable of creating pressure in the hundreds of pounds per square inch. Now, one of the coolest parts of this whole story. Inside the pipe, they regularly launch a special device the industry calls a pig. It's a big metal cylinder with rubber or polyurethane rings around the edges. Its diameter almost perfectly matches the inside diameter of the pipe. They insert the pig into a special launch chamber, close the hatch, and the fuel flow literally pushes it forward. Inside that dark pipe, this device travels hundreds of miles, pressed against the walls. It scrapes off paraffin deposits, rust, micro debris, and modern versions even scan the metal, searching for cracks and weak spots. Some of these pigs weigh hundreds of pounds and are packed with electronics like a small underwater drone. They collect terabytes of data about the pipe's condition. Then they're caught in a receiving chamber at the other end of the route, and the information gets analyzed. Now let's look at what a typical fuel journey looks like. A refinery ships a batch of gasoline into the system. It enters the pipe under high pressure. Then begins a slow but continuous journey. Flow speed, a few miles per hour. That sounds slow, but consider this. The pipe runs 24/7, no breaks. After a few days, that same batch reaches a distribution terminal. There it's received into massive storage tanks, additives are mixed in, composition gets adjusted, and then it's shipped by tanker trucks to gas stations. The driver filling up your car almost never sees the actual pipeline. But that pipeline is what delivered the fuel to his tanker. The whole system is built around risk management. Pressure sensors, leak detectors, temperature gauges, all stationed along the route. If an anomaly pops up anywhere, automation can shut down that segment in seconds. Valves slam shut. Flow stops. Problem contained. Now here's the big question. What happens if this pipeline stops for even one day? Answer: domino effect. Gas stations start running dry. Prices spike. Tanker trucks pile up in lines. Airlines scramble for alternative supplies. Businesses count their losses. All because somewhere underground, a steel artery stopped pumping. This has happened before. And every time, it becomes clear. Colonial Pipeline isn't just infrastructure. It's the hidden backbone of the economy. You don't see it every day. You don't snap photos of it for social media. But every time you turn that key in the ignition, somewhere hundreds of miles away, buried underground, a system has already been working to make that moment possible. And that's exactly why places like this deserve to be talked about. Because behind that ordinary gas pump nozzle at the station stands one of the largest engineering structures on the planet. When it comes to the scale of Colonial Pipeline, the numbers look almost unreal. Every single day, over 100 million gallons of fuel flow through this system. That means in 24 hours, this pipeline can fuel tens of millions of cars, thousands of trucks, and hundreds of planes. Roughly 45% of all the fuel consumed by the East Coast passes through this very network. The entire system stretches over 5,000 miles, with more than 50 pumping stations. Each one pushes tens of thousands of gallons per minute, keeping the liquid flowing non-stop. If even one major section drops out of the chain, supply volumes plummet by millions of gallons a day. The system serves more than 200 terminals across different states, from the Gulf Coast all the way to New Jersey. From there, fuel gets hauled out by roughly 20,000 tanker trucks every single day. Basically, every other gas station on the East Coast depends on this route in one way or another. One of the clearest examples of just how vulnerable America's fuel system is happened in 2021, when a cyber attack shut down Colonial Pipeline. Seemed like a temporary technical glitch, but the impact hit almost instantly. In less than a week, the scene at gas stations started looking like a crisis scenario. In North Carolina, over 70% of gas stations ran dry. In Georgia, nearly half the pumps sat empty. People waited in line for hours, hoarding gasoline in jerry cans, and social media flooded with videos of empty stations. Prices reacted just as fast. The cost per gallon jumped by several dozen cents in just a few days, meaning millions of drivers faced extra costs every single day. And businesses scrambled to rethink their logistics. This incident showed exactly how one shutdown of a major pipeline can flip a stable fuel market into a zone of panic and shortages in a matter of days. By the way, my body's running low on your subscriptions. According to economists, every day a system like this sits idle costs the economy hundreds of millions of dollars. Trucking companies lose out. Airlines lose out. Delivery services, all of them take a hit. A single day of downtime can delay the shipment of tens of thousands of tons of goods. Safety deserves its own conversation. Every year, hundreds of millions of dollars go into monitoring and upgrades. Along the route, thousands of pressure and leak sensors are at work. They check the pipe's condition every few seconds. In a year, the system processes billions of measurements to catch even the smallest anomalies. The pipeline also gets regular inspections using smart pig devices. In a single run, one of these tools can scan hundreds of miles of steel and detect cracks just a few millimeters wide. Thanks to that, over 90% of potential failures get fixed before they become a problem. From a financial standpoint, Colonial Pipeline is infrastructure with billions of dollars in turnover per year. The company serves hundreds of clients, from major oil traders to regional distributors. Tens of billions of dollars worth of fuel flows through the system annually. Every year, thousands of skyscrapers go up worldwide, consuming millions of tons of steel. But what actually keeps a 1,550-foot tower thinner than a pencil standing? Picture a 120-story building with a base just 82 feet wide, a 1:19 ratio. Logic says it should fall. The secret isn't in the glass or the concrete. Just 484 bolts, each costing as much as a car, hold 50,000 tons of weight. How does a small factory in Philadelphia make parts that withstand hurricanes and million-pound loads? And why could one mistake change Manhattan's skyline forever? Stick around, you'll learn what even engineers won't tell you. When I pulled up to the Hayden Bolts factory in Philadelphia's industrial district, I thought I had the wrong place. Small building, regular parking lot, nothing grand. I walked inside, and the first thing that hit me, the smell. Hot oil, superheated metal, ozone from welding. The shop floor held steady at 95 degrees Fahrenheit, even in winter. Workers in safety goggles and heavy gloves moved between machines, each one the size of my garage. Jim met me, the plant's chief engineer. Guy in his mid-50s, voice trained to cut through the roar of a press. "You here to see how we make the bolts for Central Park Tower?" he asked. I nodded. Central Park Tower, a 120-story skyscraper rising 1,550 feet. Tallest residential building in the world. But here's the crazy part. It's narrow. Base is only 82 feet wide. Height to width ratio, 1:19. It's like standing a pencil on end. Any breeze should knock it over. "Why doesn't it fall?" I asked. Jim smiled. "Because of the 484 bolts we're making right now. Each one goes 12 feet deep into the concrete foundation and holds the building's steel frame. He led me to a rack where steel rods lay. "This is where it starts," he said, pointing to a rod 4 inches in diameter and 10 feet long. "This is ASTMA 354 grade BD steel. Tensile strength, 200,000 pounds per square inch. For comparison, regular structural steel has 50,000. I picked up the rod, just to try. It weighed 145 pounds. Stage 1. Heating. The rod gets placed in an induction furnace, where it heats up to 1900 degrees Fahrenheit. At that temperature, the steel glows bright orange, almost white. When the rod reaches the right temperature, a robotic arm pulls it out and transfers it to the forging press. This press is a 50-ton monster capable of generating 1,500 tons of force. One end of the rod gets clamped into a die, and the press strikes it 4 times. Under the press strikes, the metal deforms, forming the hexagonal head of the bolt. Each strike, 250 tons of force. The steel flows into the mold, metal fibers compress, the structure becomes stronger. In 15 seconds, a shapeless rod transforms into a bolt with a head 6 inches across. I see lines running along the metal, like rivers on a map. When you strike metal properly in the right place, the fibers don't tear. They bend, they flow around the shape. That makes the head incredibly strong. Next stage, normalization. The hot bolt cools freely in a special chamber for 8 hours. If you cool it fast, internal stress builds up in the metal, and the bolt could crack under load years down the line. Slow cooling allows stable relaxation. The fibers align themselves in the optimal configuration. Then comes the most interesting part, thread rolling. We walked up to a massive machine that looked like an industrial press. "This is our main weapon," Jim said proudly. Thread rolling machine made by Feta, Germany. Costs $1,002,000. He showed me 2 steel rollers, 18 inches in diameter each. Carved into the roller surfaces were perfect grooves, the negative of the future threads. The bolt gets placed between 2 rollers. They start spinning toward each other at 50 revolutions per minute, creating 50 tons of pressure. Under that pressure, the rollers press into the bolt's surface, deforming the metal and forming the threads. "Why is this better than cutting?" I asked. Jim grabbed 2 bolts, one with rolled threads, the other cut. When you cut threads with a tool, you're slicing through the metal fibers. Look at this cut bolt under a microscope. The fibers are severed. Those are weak points. He pointed to the rolled thread bolt. But here, the fibers don't break. They bend. They follow the thread profile. The metal structure stays intact. Strength increases by 35%, and fatigue strength, the ability to withstand cyclic loads, by 60%. I ran my finger along the threads of the rolled bolt. They were perfectly smooth, without any burrs or irregularities. When the bolts tightened, the threads dig into the nuts so hard that loosening is basically impossible. This is critical for skyscrapers. They're constantly getting hammered by wind. Next stage, heat treatment. Bolts go into a furnace and get heated to 1,550 degrees Fahrenheit, then rapidly cooled in an oil bath. This is called quenching. The steel becomes exceptionally hard, but brittle. So right after quenching comes tempering. The bolts get heated again, but this time to 600 degrees and fully cooled. This removes the brittleness while keeping the hardness. The result? Perfect balance. The bolt's hard on the outside, but tough enough inside that it won't crack under impact loading. "Now for the moment of truth," Jim said, leading me into the lab. A finished bolt sat mounted on a test stand. Every 5th bolt goes through destructive testing. We take one from the batch and pull it until it breaks. The testing machine, a hydraulic press capable of generating 2 million pounds of force. The bolt gets clamped at both ends, and the press starts pulling. Numbers race across the screen. 100,000 pounds. 200,000. 300. Spec requires the bolt to withstand 1,200,000 pounds, Jim explains. The numbers climb. 800, 900, 1 million, 1 million, 200,000. Passed, the lab tech calls out, but the press keeps pulling. 1,400,000, 500, 600. Suddenly, a sharp crack. The bolt failed at 1,700,000 pounds. 42% safety margin, Jim says, satisfied. That's exactly what we need. He showed me the destroyed bolt. The failure didn't happen at the threads. Those are intact. The break is in the bolt's body, and the metal stretched before it snapped. This is ductile failure, he explains. The bolt deforms first, warning you about overload, then it breaks. That gives you time to realize something's wrong. We got back to the shop floor, where a finished batch of bolts for Central Park Tower was already laid out. 484 pieces, each 9 feet long, 130 pounds in weight. They were identical. The difference in length didn't exceed a 1/16 of an inch. How much does one of these bolts cost? I asked. Jim thought for a moment. Factoring in material, machining, testing, certification, $32,000. Yeah, that's the price of a budget car. When you're building a 100-story tower that weighs 50,000 tons and sits on a footprint smaller than a basketball court, every single part has to be perfect. Jim tells me about a recent story. In 2012, Hurricane Sandy hit New York. Winds 105 miles per hour. I was standing here thinking about our bolts in 157, the tallest residential skyscraper at the time. 105 miles per hour. That's 8,000 pounds of force per square foot of facade. The building swayed 3 feet from center. 3 feet! Today, we're going somewhere outsiders are strictly forbidden. Texas, Brownsville, international shipbreaking. Right behind me, the USS Kitty Hawk is living out its final days. A legendary aircraft carrier, a true floating fortress. Just imagine. What struck fear across the oceans for decades is now being torn apart by giant shears. Today, I'm taking you behind the scenes of this metal inferno, where they're cutting up history. You'll hear the screech of steel that'll make your ears ring. Let's go. This is gonna be huge. When a giant aircraft carrier, like the legendary USS Kitty Hawk, drops anchor for the last time off the coast of Texas in Brownsville, it's not just the end of a ship's service, it's the end of an entire era. But what happens to the very backbone of that carrier? Its anchor chain? Welcome to the graveyard of titans, a place where metal gods die to be born again. The first thing that knocks you off your feet in Brownsville isn't the heat. It's the visual weight of scale. When you see an aircraft carrier's anchor chain on deck, it looks big. When it's lying on shore, dumped in a massive pile, it looks like a scene from an apocalypse movie. The anchor chain of a Kitty Hawk-class carrier weighs as much as a full freight train. Each individual link is a steel block weighing over 330 pounds. Picture this. One ring of this chain weighs more than 2 grown men. And there are thousands of these links. When they lower this chain to the ground, it forms mountains. The height of this pile of iron easily reaches the level of a 3-story building. Standing next to it, you feel like an insect at the feet of a metal colossus. This chain held an 80,000-ton behemoth in the middle of a stormy ocean for decades, and now it looks like a motionless serpent, its skin covered in layers of rust, salt, and history. To destroy such a chain, they use giant hydraulic shears, known as shears. These are steel jaws of incredible power, mounted on heavy excavators. The process looks mesmerizing and terrifying at the same time. The operator brings the shears up to a link in the chain, steel as thick as an adult's leg. You hear only a brief crescendo of hydraulic rumble, and then a sharp, dry sound, like a gunshot. Hydraulics bite through a giant link as easily as you snap a toothpick. No sparks, no smoke, no resistance. Just pure mechanical advantage. Steel crumbles into fragments under hundreds of tons of pressure. It's the moment you realize nothing lasts forever. Even the toughest hardened steel, built for war and ocean survival, yields to the engineering genius of modern recycling. When we talk about anchor chains and hull steel from giants like the USS Kitty Hawk, we're talking top-tier metal that outperforms most of what's mass-produced today. This is high-grade steel, tempered by decades of service in the brutal ocean environment, and its journey from a Texas processing plant to the body of a brand-new Tesla. First off, you need to understand the value of the metal itself. The steel used in aircraft carriers was made to survive extreme conditions. Massive pressure, constant corrosion from salt water, colossal vibrations, and temperature swings. This isn't the metal they make tin cans from. This is low-alloy, high-strength steel that produces minimal waste during recycling and practically doesn't lose its physical properties after remelting. Economically speaking, recycling a carrier in Brownsville is like mining pure gold in the world of ferrous metallurgy. Every ton of this metal is far more valuable than ordinary scrap because it requires less purification and fewer additives when creating new alloys. The transformation process begins with pieces of chains and hull plating cut by hydraulic shears being loaded into giant buckets and sent to steel mills. The main character at this stage? The electric arc furnace. Unlike outdated blast furnaces that need ore and coal, electric arc furnaces run primarily on scrap. It's the perfect machine for rebooting metal. When multi-ton chunks of aircraft carrier chain hit this hellish circle, an arc flashes between the graphite electrodes at over 5,000 degrees Fahrenheit. In that blinding light, the ship's past literally evaporates. Rust, paint, and salt float to the surface as slag, while pure, molten top-grade steel settles at the bottom. This is the moment the economic future is born. Thanks to the high purity of the starting material, steelmakers can tune this melt for specific orders with minimal cost. If the market needs ultra-strong steel for the auto industry, they add precise doses of alloying elements to the furnace. And this is where Tesla comes in. Modern automotive manufacturing, especially electric vehicle production, demands metal with a perfect balance of weight and strength. Steel that once held a crew of thousands aboard an aircraft carrier through violent storms now becomes safety pillars, suspension components, or structural frames for electric cars. It's a remarkable paradox. A former symbol of military might that burned thousands of gallons of fuel oil per hour is reborn as environmentally clean transportation running on electricity. But automobiles are only part of the story. A huge portion of high-grade steel from Texas shipyards flows into the construction sector. Modern skyscrapers in Dubai, New York, or Shanghai need rebar and beams capable of withstanding colossal static and wind loads. Using recycled aircraft carrier steel in construction isn't just about cost savings, it's about prestige and environmental responsibility. Today's architects and developers fight tooth and nail for LEED certifications, awarded for using recycled materials. So the steel backbone of the old USS Kitty Hawk literally becomes the backbone of a new financial center or luxury residential complex. The economic logic of this process is backed by a global push toward decarbonization. Producing steel from scrap in electric arc furnaces emits 70 to 80% less carbon dioxide than traditional production from ore. For big corporations like Tesla or construction giants, this is critical for their sustainability reports. In other words, when they buy a chopped-up aircraft carrier, they're not just buying metal, they're buying green points for their reputation. Ultimately, this transformation carries deep philosophical and financial undertones. The carrier steel was purchased with taxpayer money decades ago as an investment in national security. Now, through the recycling process, that investment returns to the civilian economy. And have you subscribed to the fascinating space of my channel yet? If not, now's the perfect time. Once electric arc furnaces melt down the carrier's steel, it emerges as glowing ingots or continuous strips, ready for a new life. Thanks to its exceptional purity, This metal becomes the foundation for critically important components, from ultra-strong truck axles bearing tons of cargo to surgical instruments or intricate parts of aircraft engines. Some of the metal gets transformed into massive I-beams that'll become the skeletons of new stadiums or bridges, capable of standing for centuries. There's a real irony here. Steel that was once created to carry planes and cannons is now being reborn as tools of creation. From the blade of a kitchen knife in your home to high-tech medical equipment that saves lives. When you look at those giant hydraulic shears in Brownsville, you're not just seeing destruction. You're seeing the first stage of creating something new. Every yard of chain that gets cut is a contribution to the foundation of a future skyscraper, or the body of the next technological breakthrough on wheels. This is the true graveyard of titans, where every death is just the beginning of a new, longer, and more useful life. Right now, you're holding the result of an African tragedy in your hands. Inside your smartphone, laptop, gaming console are tiny components made from a metal mined in the jungles of Congo, where actual wars are fought over it. This is Coltan, a dull black rock that looks like an ordinary river stone but costs thousands of dollars per pound, and without which no modern electronics would work. Millions of people have been killed for this rock. Its extraction finances armed groups, destroys guerrilla reserves, and turns people into slaves. But without it, your phone wouldn't exist. Let's peer into the dark world of the most controversial mineral of the digital age, where every like and every post carries the price of a human life. First, the terminology. Coltan isn't an official mineral name. It's short for columbite tantalite. It's an ore containing two metals, niobium, which used to be called columbium, and tantalum. It's tantalum that makes coltan so valuable. It's a silvery gray metal with a unique combination of properties. It doesn't corrode at all, withstands extreme temperatures, has high capacitance, and barely conducts electricity because of a thin oxide film on its surface. That last property revolutionized electronics. Tantalum is used to make capacitors, components that store and discharge electrical charge. Tantalum capacitors are microscopic, the size of a grain of sand, but they have enormous capacitance. They're stable, reliable, work for years without degrading. Every smartphone contains 40 to 50 tantalum capacitors. A laptop, up to 100. Gaming consoles, cameras, even electric toothbrushes. Tantalum's everywhere. Coltan looks like black or dark gray rock with a metallic shine. Heavy, density around 8 grams per cubic centimeter, almost like lead. If you pick up coltan, you feel it's unusually heavy for its size. It occurs as coarse crystals or grainy masses in granite formations. Nothing special to look at, just a rock. But you can get anywhere from $100 to $400 per kilogram, depending on tantalum concentration. The main problem with coltan is geography. About 60% of the world's reserves are in one place. The eastern provinces of the Democratic Republic of Congo, especially Kivu and Ituri. This is one of the most dangerous regions on the planet. For decades, there's been a civil war involving dozens of armed groups that control the mines and use the profits to buy weapons. The story of the coltan rush began at the turn of the millennium. In the early 2000s, demand for tantalum exploded due to a boom in mobile phone and gaming console production. Sony released the PlayStation 2, Nokia and other manufacturers were churning out millions of phones. The price of coltan skyrocketed from $30 to nearly $400 per kilogram. A real gold rush started in Congo, only black. Tens of thousands of people dropped everything and headed into the jungle to dig for coltan. Armed groups seized control of the deposits. Murders, rapes, forced labor began. Kahuzi-Biega National Park, home to mountain gorillas, was overrun by miners. Animals were killed for meat, or simply because they got in the way. The gorilla population plummeted by 90% in just a few years. The UN published a report confirming that coltan sales were financing a conflict that had claimed millions of lives, the bloodiest war since World War II. Armed groups controlled the mines, forcing local populations to work for free or for pennies, smuggling coltan through Rwanda and Uganda, selling it to middlemen who shipped it to China and Europe for processing. Coltan extraction in Congo is mostly artisanal, meaning small scale, no machinery. Miners work in rivers and streams, washing ore in pans like gold prospectors. Coltan's heavier than regular sand and pebbles, so it settles at the bottom of the pan. Or they dig pits in the forest, sometimes 30 feet deep, with no reinforcement. Cave-ins kill people regularly, but nobody keeps track. The working conditions are horrific. People stand waist-deep in murky water all day long, washing tons of rock for just a few pounds of coltan. They make $1 to $5 a day, more than farming, but still poverty. No safety, no rights. Kids work right alongside adults. Women are forced into labor or worse. Coltan gets collected, dried, and sold to local traders. They haul it to regional centers where Chinese and other foreign companies have warehouses. There, they weigh the coltan, test the tantalum concentration with handheld analyzers, pay cash. Then they ship it out by plane or truck through neighboring countries, Rwanda, Uganda, Burundi, to mask where it came from. Rwanda officially exports hundreds of tons of coltan every year, even though it has almost no deposits on its territory. It's obvious what's happening. It's a transit point for Congolese coltan. The international community knows, but stopping the flow is hard. Borders in the region are porous, corruption thrives, tracing the origin of a specific shipment is nearly impossible. The coltan gets shipped to China, where most of the processing facilities are concentrated. There, it's melted in electric arc furnaces at temperatures exceeding 3,600 degrees Fahrenheit. What comes out is slag containing tantalum and niobium oxides. This slag gets treated with hydrofluoric acid, producing fluorides, which are then reduced to metals through complex chemical processes. Tantalum is incredibly refractory. Its melting point is around 3,000 degrees Celsius, third highest after tungsten and rhenium among all elements. That makes processing energy intensive and complex. Extracted tantalum is converted into powder, which is then pressed, sintered, and turned into anode foils for capacitors just a few micrometers thick. A tantalum capacitor works simply. Thin foil is coated with an even thinner film of tantalum oxide, which acts as the dielectric. Thanks to the microscopic thickness of this film and the massive surface area of the porous structure, you get enormous capacitance in a microscopic volume. This allows electronics to be compact. Without a tantalum capacitors, smartphones would be the size of bricks. Legal coltan mining exists. Australia, Brazil, Canada have deposits and extract coltan using industrial methods that comply with environmental and labor standards. But the cost is higher because you have to pay decent wages, maintain safety standards, and rehabilitate the land. Congolese coltan, extracted through what's essentially slave labor, is cheaper, so demand for it persists. There are also synthetic alternatives. Ceramic capacitors based on barium titanate can replace tantalum capacitors in some applications. They're cheaper and aren't linked to conflict. But for the most compact devices with high reliability requirements, tantalum remains irreplaceable. Military electronics, medical implants, aerospace equipment, they only use tantalum. Tantalum demand holds steady, around 2,000 tons a year. That doesn't sound like much compared to the millions of tons of copper or steel, but given its rarity and concentration in one region, even that amount creates enormous pressure. Every new smartphone, every data center, every 5G cell tower requires tantalum capacitors. Tantalum prices fluctuate between $150 and $300 per kilogram for the metal, or the equivalent for ore depending on concentration. For comparison, gold runs about $60,000 per kilogram. Tantalum's cheaper, but you need way more of it. And extraction is concentrated in a conflict zone, making it strategically critical. The environmental fallout is horrific too. The Congo jungle, one of the planet's largest tropical rainforests after the Amazon, is home to unique species. But artisanal mining is wrecking ecosystems. Forests get chopped down for mines and miner camps. Rivers become polluted with washed-out rock that kills fish and aquatic life. Poaching thrives. Miners hunt wild animals for food. There are attempts to recycle tantalum from electronic waste. Old cell phones, computers, devices contain tantalum capacitors. Technologies exist to extract and recycle them, but economically it's tough. You have to collect massive quantities of old devices, disassemble them, isolate tiny components, remelt everything. Right now, only 5 to 10% of tantalum comes from recycling. Some activists are calling for a boycott of electronics, or at least mindful consumption. Don't swap your smartphone every year. Repair instead of tossing it. Buy used. But here's the reality. Most people don't even know about coltan and the problems tied to it. Manufacturers don't advertise the dark side of their shiny gadgets. There's hope in technological progress. New types of capacitors are being developed that could eventually replace tantalum ones. Graphene supercapacitors promise even higher capacity in smaller sizes. But mass production is years, maybe decades, away. For now, tantalum remains a critical element of the digital age. The irony? Congo is one of the poorest countries in the world, despite its incredible wealth of natural resources. Cobalt, coltan, copper, gold, diamonds, all buried in Congo's soil. But corruption, conflict, and exploitation by foreign companies mean that wealth never reaches the people. It's a classic resource curse, when natural resources become not a blessing, but the cause of endless wars and suffering. Picture a liquid that goes through at least 10 different transformations before it ends up in the tank of a truck, tractor, or generator. It's boiled, compressed, broken down into molecules, reassembled, cleaned with hydrogen, and tested dozens of times. All of this so an engine can run for hours under load, in scorching heat and freezing cold, without failures or surprises. Diesel fuel seems ordinary, but it's actually one of the most complex products of modern industry, where behind every gallon stands engineering, temperature, and cold calculation. Diesel fuel doesn't just appear from crude oil, like gasoline from a pump. It's the product of a long, hot, and highly controlled chain of processes, where crude oil is gradually transformed from a dark, heavy liquid into a precisely defined mixture of molecules capable of running reliably in an engine. Everything starts with oil, but then it's literally broken down into components, sorted, cleaned, and reassembled, this time in the right form. Crude oil begins its journey far from the refinery, at oil fields, where it's lifted from the Earth's depths through wells. Along with the oil, water, gas, sand, and small rock particles come to the surface. So right at the extraction site, it's partially settled and the largest impurities are separated out. Once it's out of the ground, the oil hits the road. Most of the time, that means pipelines, continuously pumping millions of tons of liquid across hundreds, even thousands of miles. Where there are no pipes, tankers or rail cars take over. Either way, by the time the oil reaches the refinery, it's still far from ready. Before processing can begin, the crude has to be prepped. It almost always contains water, dissolved salts, and solid particles. Leave those in, and they'll wreck the equipment fast. Salts cause corrosion, water messes with stable heating, and solids wear down pumps and pipes. So the oil gets heated and run through desalting and dehydration units. There, it's mixed with fresh water to wash out the salts, then an electric field forces the water to separate and settle. After that, the crude is much cleaner, and a lot safer for what comes next. The prepared crude oil enters the refinery's main unit, the atmospheric distillation column. This is a tall metal tower, like a multi-story building, with dozens of horizontal trays or packing material inside. The column maintains a constant temperature difference. It's super hot at the bottom, and the higher you go, the cooler it gets. The oil is first heated intensely in furnaces, usually to around 660 degrees Fahrenheit, and then injected into the middle of the column in this hot state. Once inside, the oil starts behaving completely differently than it did in the pipeline. It partially vaporizes, creating a mixture of vapor and liquid. Lighter components with lower boiling points quickly turn to vapor and rise upward. Heavier fractions stay lower or flow all the way down to the bottom. Each level of the column corresponds to its own temperature range, so the vapors condense exactly where they're comfortable. As a result of this process, crude oil is essentially taken apart
where it
into its
remains
components.
hottest, settle
The lightest
lubricating
fractions
oils and
collect at
heavy
the top,
residues.
medium ones below, and the heavy residues remain at the very bottom. Everything happens without chemical reactions. The molecules don't break down or change. They simply separate based on physical properties. It's from this point that the real life of crude oil begins as raw material for fuel, lubricants, and dozens of other products, because each fraction obtained will follow its own technological pathway. This is where diesel fraction first appears. It's heavier than gasoline and kerosene, so it condenses lower down, but it's still light enough to be a liquid fuel. This isn't finished diesel fuel yet, just a halfway point: gas oil. It packs a lot of useful energy, but also plenty of sulfur, nitrogen compounds, and unstable molecules that engines hate. The gas oil that comes out of crude distillation is still miles away from the diesel fuel you pump into your tank. It looks similar, sure, but its makeup is dirty by modern standards. It contains sulfur, nitrogen compounds, traces of metals, and unstable hydrocarbon chains that oxidize easily and form carbon deposits. If you fed this stuff straight into an engine, it would quickly destroy the injectors, catalytic converters, and exhaust cleaning systems. That's exactly why gas oil has to go through a hydro-treating stage. At this stage, the fuel gets channeled into special reactors where they create extremely harsh conditions. Temperature there typically hits several hundred degrees, and pressure runs dozens of times higher than atmospheric. Hydrogen gets fed into the gas oil, and this mixture passes through a catalyst bed. The catalyst doesn't get consumed in the process, but it's what forces the chemical reactions to go fast and in the right direction. Without it, purification would either be way too slow or just flat out impossible on an industrial scale. When the gas oil contacts the hydrogen, a series of reactions kicks off. Sulfur-containing compounds break down, and the sulfur converts into hydrogen sulfide, a gas that's easy to separate from the fuel. Nitrogen compounds transform into ammonia, which also gets removed from the stream. At the same time, hydrogen heals unstable molecules. Double bonds get saturated, and fragile structures rearrange into more stable ones. As a result, the fuel becomes chemically calmer, oxidizes less during storage, and behaves better during combustion. After the reactor, the gas oil is cooled and sent to separation units. There, gaseous products, hydrogen sulfide, ammonia, excess hydrogen, are separated from the liquid fuel. Hydrogen is usually recycled back into the process, while harmful gases are sent for further processing or neutralization. It's thanks to this stage that sulfur content in diesel fuel drops by tens or even hundreds of times, down to levels that meet modern environmental standards. The importance of hydrotreatment can't be overstated. It doesn't just cut harmful emissions, it directly impacts engine life. Cleaner fuel puts less wear on fuel injection systems, doesn't poison catalytic converters and particulate filters, burns more consistently, and keeps the engine running predictably. This is really the stage where gas oil stops being a semi-raw material and starts becoming actual diesel fuel suitable for 21st century machinery. But the process doesn't end there. Some diesel components don't even come from primary distillation. Heavy petroleum residues go through vacuum distillation, where reduced pressure extracts even more useful fractions. And if that's still not enough, cracking enters the picture, a process where large, lazy molecules are literally broken down into smaller ones. Hydrocracking is especially critical for diesel because it produces fuel with better combustion characteristics, a higher cetane number, and fewer impurities. After all these stages, different diesel components get blended together. This isn't some random pouring from one barrel to another. It's precise recipe-based mixing. Engineers dial in the proportions so the fuel meets standards. Good ignition, no thickening in the cold, minimal smoke, and no damage to the fuel system. At this stage, they add additives, tiny amounts, but with big impact. They improve lubrication properties, protect against corrosion, reduce foaming, and help the engine start up in winter. Seasonality is a whole different story. Summer diesel is thicker and more stable in warm temperatures. Winter diesel undergoes additional processing. Components that could crystallize in the cold are removed or modified. Otherwise, at 14 degrees Fahrenheit, the fuel starts turning into a cloudy sludge that clogs the filters. For extremely cold regions, they make Arctic diesel, lighter, pricier, and way more complex to produce. Once the fuel's ready, it's stored in tanks, then shipped to fuel depots, and finally to gas stations. But even along that route, it can still be tested, filtered, and adjusted. Diesel isn't a product where you can afford close enough. One small mistake at the refinery can turn into widespread equipment failures.